December 23, 1944. The snow-covered hills outside Bastogne, Belgium. Obergefreiter Klaus Werner pressed himself into the frozen earth as the first shells began to fall. Not the single impacts he had learned to anticipate, not the scattered bursts that gave men time to dive for cover. This was different. The sky above him erupted simultaneously. Dozens of explosions materialized in the same instant, 20 feet above the ground, turning the air itself into shrapnel. Werner never heard the whistle of incoming rounds. There was only the sudden transformation of winter silence into hell. The young German soldier had survived 2 years on the Eastern Front. He had endured Stalingrad's ruins and the grinding retreat across Ukraine. He knew artillery. But this was something else entirely. The shells exploded before hitting the ground, each burst creating a cone of death that scoured the earth below. Men who had thrown themselves prone found no protection. The shrapnel came from above, penetrating foxholes, punching through helmets, tearing through bodies that had survived Russian barrages and partisan ambushes. Werner crawled toward a crater, his ears ringing, his mind struggling to process what was happening. Around him, his company was being systematically destroyed. Not by the slow attrition of conventional artillery, not by the terror of rocket barrages. This was surgical, precise, overwhelming. Within 3 minutes, 70% of his unit was dead or wounded. The survivors huddled in whatever cover they could find, knowing that another barrage could arrive at any moment with the same devastating simultaneity. He would later tell American interrogators that this moment, more than any tank assault or air raid, convinced him Germany had lost the war. The nation that could coordinate artillery fire with such mathematical precision possessed capabilities that made continued resistance meaningless. What Werner experienced was the culmination of American artillery doctrine, a system so sophisticated that it transformed 19th century cannon into 20th century instruments of industrial warfare. While the German military had focused on tanks and tactical air power, the United States had quietly revolutionized the oldest weapon on the battlefield. They had taken artillery and rebuilt it from the ground up, creating a system that German commanders would come to fear more than anything else in the American arsenal. The story of American artillery superiority begins not on European battlefields, but in the red Oklahoma clay of Fort Sill. Throughout the 1930s, while Germany rebuilt its military and Japan expanded across Asia, a group of American artillery officers were rethinking everything about how armies deliver firepower. They were led by men like Carlos Brewer, the director of gunnery, who abandoned traditional methods of massing fire by terrain features or grid coordinates. Brewer and his team introduced the firing chart, adopted survey methods for locating battery positions, and designated targets with reference to base points. These seemingly technical changes represented a philosophical revolution. Traditional artillery required forward observers to spot shells and call adjustments. A battery might fire ranging shots for 10 minutes before achieving accuracy. Each gun operated somewhat independently. The result was firepower that arrived gradually, giving enemy troops time to seek cover. Brewer's team understood that artillery's lethality depended not just on the number of shells, but on when they arrived. The first few seconds of a barrage produced the most casualties. After that, soldiers went prone or found cover, dramatically reducing the effectiveness of subsequent rounds. Research conducted in the 1970s would later quantify what Fort Sill instructors understood intuitively. A study called troop reaction and posture sequencing determined exactly how fast soldiers could achieve protective postures when artillery fire began. At the moment of first impact, only 9% of soldiers were prone, 33% had achieved some cover, but 58% were still standing. Within 2 seconds, the standing figure dropped to 29% as soldiers threw themselves down. After 8 seconds, all soldiers were prone with whatever additional cover they could find. The implication was clear. The first 3 seconds of artillery fire inflicted approximately 2/3 of all casualties. Everything after that was dramatically less effective. The solution was elegant in concept, but extraordinarily difficult in execution. What if multiple batteries, miles apart, could fire at the same target with their shells arriving simultaneously? The technical challenges were immense. Each gun had different distance to the target. Each battery had variations in altitude, wind, temperature, barrel wear all affected shell trajectories. To coordinate dozens of guns firing at different times, so their shells converged on a single point within a 3-second window, required calculations that seemed impossible in the chaos of combat. Fort Sill's gunnery department solved it with mathematics and organization. They developed fire direction centers, nerve nodes where trained specialists could calculate firing solutions for multiple batteries simultaneously. The FDC concept represented a fundamental reimagining of artillery employment. Rather than treating each battery as an independent unit, the FDC integrated all artillery assets within a given area into a single coordinated weapon system. Specialists at the FDC would receive target information from forward observers, calculate firing data accounting for all variables, and transmit firing commands to each battery. Each gun would fire at a precisely calculated moment based on its distance from the target and the flight time of its shells. It worked. Multiple batteries fired at carefully calculated intervals, their shells arriving at the target in a compressed time frame that gave enemies no chance to react. The demonstration was witnessed by senior army officers who immediately recognized its significance. This was not just an incremental improvement, it was a transformation in the fundamental nature of artillery employment. The doctrine was called Time on Target, abbreviated TOT. During training, an FDC would broadcast a countdown to all participating batteries. Each battery calculated the time of flight from their guns to the target. They fired during the countdown at the precise moment that caused their rounds to arrive simultaneously with rounds from every other battery. The effect on ground troops was devastating. One moment, silence. The next, dozens or hundreds of shells exploding in concert, saturating an area with simultaneous destruction. The development of this capability required far more than just mathematical innovation. It demanded reliable communications networks that could function under combat conditions. It required survey teams that could precisely locate battery positions even during rapid advances. It needed forward observers trained not just in calling fire, but in understanding the capabilities and limitations of the entire artillery system. Most critically, it required a level of organizational discipline that ensured every battery, every FDC, every forward observer operated according to standardized procedures that made coordination possible. By 1944, American artillery had refined this capability to an art form. Fire direction centers existed at battery, battalion, brigade, and corps levels. Higher-level FDCs monitored subordinate units' missions and could coordinate fire from multiple battalions or even entire corps. In training exercises, as many as 72 guns from 3 battalions could put steel on target in a single coordinated strike. The rule was simple: silence is consent. If a subordinate unit did not hear a cancel order from higher command, the mission proceeded. The layered structure meant that a single forward observer with a rifle company could theoretically bring down the concentrated fire of an entire corps. The request would go to the battalion FDC, which would assess whether battalion assets were sufficient. If not, the mission would escalate to division FDC, then corps. At each level, fire direction specialists would calculate which batteries could participate, coordinate timing, and broadcast firing data. The theoretical response time was 3 minutes for battalion fire, 6 minutes to include division assets, and 9 minutes for a full corps-level TOT strike. In practice, these times were often achieved. Forward observers in Italy reported calling fire missions and having shells arrive within 4 minutes. In France, during the breakout from Normandy, observers noted that emergency fire missions could be fulfilled in under 3 minutes. This responsiveness gave American infantry enormous confidence. They knew that if they encountered strong resistance, artillery support was minutes away, not hours. They knew that the artillery would arrive precisely where called, not scattered across a wide area. They knew that the weight of fire would be overwhelming. The equipment itself was excellent. American howitzers and guns were slightly heavier than German equivalents, but generally had longer range. The M1 105mm howitzer became the workhorse of divisional artillery, reliable and accurate. With a range of over 7 miles, it could fire a 33-pound high-explosive shell that was effective against personnel, light fortifications, and vehicles. The M1 155mm howitzer provided heavier punch, throwing a 95-pound shell over 9 miles. For truly long-range work, The M1 55mm long ton could hurl a 107-pound projectile over 13 miles. The M1 8-inch gun fired 250-pound shells more than 20 miles. For truly massive firepower, the M1 250mm howitzer could throw 360-pound shells over 14 miles. American artillery was almost completely motorized. German artillery still relied heavily on horses for movement well into 1944. An American heavy artillery battalion could road march up to 160 miles per day. When the situation changed, American batteries could displace and resume firing with remarkable speed. German Field Marshal Erich von Manstein, fighting on the Eastern Front, noted with grudging admiration how American trucks dramatically increased the mobility of Soviet artillery units after Lend-Lease deliveries began. The M4 high-speed tractor could tow the heaviest American guns at speeds exceeding 35 miles per hour on roads. Even in difficult terrain, these tractors maintained mobility that horse-drawn German batteries could not match. A German artillery battery that took hours to displace and move to a new position could be caught by American counter-battery fire. An American battery using M4 tractors could be firing from a new location before German counter-battery assets even located their previous position. The sophistication of American fire direction impressed even enemies. In February 1943, Erwin Rommel wrote to his wife describing the fighting in Tunisia. He specifically mentioned how American observation planes directed the fire of numerous batteries on all worthwhile targets throughout the zone. This coordination, which seemed almost casual to American forces, represented capabilities the Wehrmacht could not match. Rommel, who had defeated British forces in North Africa repeatedly, found himself facing an enemy whose artillery capabilities exceeded anything he had previously encountered. American forward observers were integrated directly into infantry units. They moved with the rifle companies, identifying targets, calling fire missions, adjusting rounds. Communication was constant and reliable thanks to American radio production. An infantry commander could call for artillery support and have shells landing within minutes. If the situation required massive firepower, the request would cascade up through fire direction centers until corps-level assets were engaged. The radio networks themselves represented significant technological achievement. American industry produced portable radios that were reliable, relatively lightweight, and capable of operating under field conditions that would have destroyed earlier equipment. Forward observers carried radios that could reach battalion FDCs from several miles away. Battalion FDCs had more powerful radios that networked with division and corps. The entire system functioned as an integrated communications network that could coordinate hundreds of guns across dozens of miles. Training was equally important. American forward observers underwent extensive schooling that taught not just radio procedures but the fundamentals of artillery science. They learned to estimate distances, read terrain, understand how weather affected shell trajectories. They practiced calling fire missions until the procedures became automatic. By the time they joined infantry units in combat, they could accurately assess targets, determine what type of artillery fire was needed, and communicate requirements to FDCs with professional precision. The ammunition supply was equally impressive. American industry produced artillery shells in quantities that German commanders found incomprehensible. A single American artillery battalion might expend more ammunition in a day than some Wehrmacht divisions received in a week. Batteries could fire sustained bombardments that would have exhausted German ammunition stocks in hours. During the Rhine crossing in March 1945, General William Simpson's 9th Army opened the attack with 2,070 guns firing along the river. They maintained a rate of 1,000 rounds per minute, expending over 65,000 shells in the opening barrage. Observers watching from behind the lines saw the entire western bank of the Rhine lit by continuous muzzle flashes, a demonstration of industrial firepower that had no precedent in military history. The logistics required to sustain this level of fire were staggering. Each 105mm shell weighed 33 pounds, each 105mm shell weighed 95 pounds. To fire 65,000 shells required moving thousands of tons of ammunition from depots to batteries under combat conditions. American logistics units accomplished this routinely, using fleets of trucks that operated around the clock. German logistics, dependent on horse-drawn wagons and increasingly disrupted rail networks, could not match this capability. German prisoners consistently cited American artillery as the most feared aspect of U.S. combat power. Captured soldiers told interrogators that they were less impressed by American armor or infantry tactics than by the overwhelming, precisely coordinated artillery fire that could arrive without warning. One German officer noted that American infantry seemed to maneuver just enough to locate enemy positions, then called in artillery to do the actual killing. Traditional fire and maneuver doctrine had been replaced by maneuver and fire, a fundamentally different approach that leveraged America's industrial and organizational strengths. This observation was accurate. American infantry tactics evolved throughout the war to emphasize the use of artillery. When encountering resistance, American infantry commanders were taught to fix the enemy position, withdraw slightly, and call for artillery. The artillery would destroy or suppress the position, and infantry would then advance to occupy it. This approach minimized American casualties while maximizing the effectiveness of America's artillery advantage. German infantry, trained in aggressive assault tactics, found themselves repeatedly pinned by American defensive fire and then destroyed by artillery they never saw. General George Patton, never one to mince words, told a French army friend that the poorer the infantry, the more artillery it needs, and the American infantry needs all it can get. This was not criticism of the infantry so much as recognition that American doctrine had evolved to emphasize coordinated firepower over small unit tactics. Why risk soldiers in close combat when artillery could destroy enemy positions from miles away? Most American combat commanders agreed that artillery was the outstanding branch of the ground forces. The 12th Corps artillery that fought under Patton's Third Army was described as the hammer that drove the steel spikes of the 12th Corps into the coffin of the Third Reich. This was not hyperbole. 12th Corps artillery repeatedly demonstrated capabilities that German forces could not counter. During the advance through France, 12th Corps artillery fired time-on-target missions that coordinated more than 600 guns simultaneously. The concentrations were so devastating that German units caught in them effectively ceased to exist as organized formations. The system reached its apex with the introduction of the proximity fuse in late 1944. This device, developed in absolute secrecy, represented one of the war's most important technological innovations. Traditional artillery shells exploded either on contact or after a preset time delay. Contact fuses required direct hits. Time fuses required accurate prediction of shell flight time and precise setting before firing. Both methods had severe limitations. A shell that missed its target by yards was wasted. A time fuse set incorrectly might explode harmlessly above or after passing through enemy formations. The VT variable time proximity fuse solved these problems through radio technology. A miniature transmitter in the fuse broadcast a signal. When the shell approached the ground or a target, the reflected signal triggered detonation. The shell exploded 20 to 50 feet above ground, creating an airburst that showered shrapnel over a wide area. There was no protection. Soldiers in foxholes, troops behind cover, men who had gone prone, all were vulnerable to the downward cone of destruction. Developing a radio transmitter that could survive being fired from a gun barrel was extraordinarily difficult. Artillery shells experienced acceleration exceeding 5,000 G when fired. They spun at nearly 30,000 RPM from the rifling. The centrifugal forces and acceleration would destroy conventional electronic components. The miniature vacuum tubes needed to be specially designed and manufactured to tolerances that challenged even America's advanced electronics industry. The solution required years of development. Working with Western Electric and Raytheon, researchers modified hearing aid tubes to create ruggedized components. The tubes were redesigned with heavier filament supports, thicker glass envelopes, and internal structures that could withstand the massive forces. Even the solder connections required special techniques to prevent them from breaking under stress. Each fuse contained components that represented the cutting edge of miniaturization and ruggedization technology. Testing proved the concept's value, but also revealed the challenges. Early test models showed only 52% reliability, more than half failed to function properly. The US Navy accepted this failure rate because even imperfect proximity fuses dramatically improved effectiveness. A 52% success rate meant that half of all shells became significantly more lethal. For anti-aircraft use, this was acceptable. Further refinement improved reliability to over 70% by 1944. Testing in August 1942 provided dramatic proof. The cruiser USS Cleveland fired proximity-fused shells at radio-controlled drone aircraft over Chesapeake Bay. The test was scheduled for 2 days. It ended on the first day when all 3 target drones were destroyed with just 4 shells. Traditional anti-aircraft fire required hundreds or thousands of rounds to destroy a single aircraft. Proximity fuses reduced this to single-digit numbers of shells. The improvement in effectiveness was almost incomprehensible. The device was so revolutionary that its existence remained classified at the same level as the Manhattan Project. Pentagon officials feared that if Germany captured a proximity fuse, their engineers would reverse engineer it and develop countermeasures. German proximity fuses could devastate Allied bomber formations or neutralize the tactical advantage American forces enjoyed. The classification was so strict that even discussing the fuse's existence was forbidden. Workers manufacturing components did not know what they were building. Security was absolute. American forces were initially forbidden from using the fuses in any situation where they might be captured. They were restricted to naval anti-aircraft use over open water, where any dud shells would sink. This restriction was enforced rigidly despite pressure from field commanders who understood the fuse's potential against ground targets. The risk of German capture and reverse engineering was considered too high. The restriction lifted gradually as the strategic situation evolved. In June 1944, proximity fuses were authorized for use against V-1 rockets attacking London. The results were dramatic. By the end of August, anti-aircraft batteries equipped with VT fuses destroyed 79% of all incoming rockets. The proximity fuse saved London from systematic destruction. On the last day of heavy V-1 attacks, radar detected 104 missiles approaching the coast. Proximity-fused shells destroyed 68 of them. Only 4 reached London. The improvement over previous anti-aircraft effectiveness was decisive. When German V-1 attacks shifted to Antwerp in September 1944, the British 11th Armoured Division defending the city urgently requested proximity fuses. The port of Antwerp was critical to Allied logistics, and V-1 attacks threatened to close it. The devices were rushed into production at the Crosley Corporation in Cincinnati, and Prime Minister Winston Churchill personally authorized a special flight of Lancaster bombers to transport them across the Atlantic. The urgency reflected Antwerp's strategic importance and confidence that the fuses would be effective. Once deployed, a single anti-aircraft unit in Antwerp destroyed 48 of the first 75 V-1 rockets they encountered. The port remained operational for the rest of the war. For ground use, the embargo remained until December 1944. The Battle of the Bulge changed everything. On December 16, German armor broke through American lines in the Ardennes, launching Hitler's last major offensive in the West. General Dwight Eisenhower, commanding Allied forces in Europe, immediately demanded authorization to use proximity fuses against ground targets. The tactical situation was critical. German forces had achieved surprise and were advancing rapidly. Eisenhower needed every advantage. The Pentagon relented. The risk of German capture was now acceptable given the strategic stakes. Within 2 days, proximity-fused shells were being fired at German formations. Over 200,000 shells equipped with VT fuses, codenamed POZD, were rushed to the front. American artillery battalions received crash training on handling and firing the new ammunition, ETILD-GES. The fuses required no special procedures. They were simply used in place of conventional fuses, but gunners needed to understand their capabilities. The effect was catastrophic for German troops. On Christmas night 1944, Patton's Third Army caught a German battalion crossing the Sauer River near Echternach. American artillery opened fire with proximity-fused shells, CHE. The German soldiers, experienced on the Eastern Front, reacted as they had been trained, going prone and seeking minimal cover. It made no difference. The shells exploded above them, creating overlapping kill zones. When American forces advanced, they counted 702 German dead in a small area. The precision of the count speaks to the thoroughness of the destruction. Bodies were concentrated in a relatively small zone, killed by shrapnel that had come from directly above. There were no wounded. The fury of the bombardment had left only dead, and those fortunate enough to have been outside the impact area. German soldiers had no defense. Traditional artillery could be countered by going prone, finding cover, digging deeper foxholes. Proximity fuses made these responses futile. The shells exploded at optimal height automatically, without requiring prediction or adjustment. Every shell became an airburst. Foxholes that had protected against conventional artillery became death traps as shrapnel rained down from above. Troops who went prone found themselves more exposed, not less, to the downward cone of fragments. There was no tactical countermeasure, no training that could help. Soldiers simply died. The psychological effect was as important as the physical casualties. German troops, already demoralized by the failure of the Bulge offensive, faced a weapon for which they had no tactical answer. Veterans who had survived years on the Eastern Front found themselves helpless against a technology they could not understand. The randomness was crushing. A soldier might survive one proximity bombardment through pure luck, only to die in the next. There was no skill that improved survival, no heroism that mattered. Men simply waited for shells to arrive and hoped they would not be in the kill zone. Interrogations of German prisoners after the Bulge repeatedly mentioned the new American artillery. One prisoner described the attacks as quick, powerful bursts for which there was simply no defense. The shells arrived without warning, exploded above ground before troops could react, and saturated large areas with simultaneous detonations. German officers noted that their men increasingly refused orders to advance across open ground. The fear was not of death. German soldiers were veterans who had accepted mortality, but of helpless death, of being torn apart by a weapon that could not be avoided or countered through skill or courage. During the Battle of the Bulge, Germans briefly captured an American ammunition depot containing 20,000 proximity fuses. This was precisely the scenario Pentagon officials had feared. German engineers immediately began examining the devices. They disassembled several, studied the components, and attempted to understand the operating principle. Their conclusion was astonishing. They decided that proximity fuses were impossible. The miniature electronics could not, in their assessment, survive the stresses of being fired from artillery. The G-forces would destroy any vacuum tube. The centrifugal forces would tear apart any circuit. The Germans assumed the fuses served some other purpose, perhaps related to anti-tampering or self-destruct mechanisms. They never recognized what they had captured. This failure reflected not German incompetence but the enormous gap in electronics manufacturing capability. American industry had developed techniques for miniaturization and ruggedization that German industry simply could not match. The Germans had attempted to develop proximity fuses. More than 30 different designs were researched, but none succeeded because they lacked the manufacturing sophistication to produce components that could survive artillery firing. Even if German engineers had correctly identified the fuse's purpose, reverse engineering would have been extremely difficult. The fuses represented not just clever design but advanced manufacturing processes. The miniature vacuum tubes required specialized equipment to produce. The assembly required precision that challenged even American factories. Germany, with its industry under constant bombing and its skilled workforce increasingly depleted, could not have replicated American fuse production even with complete technical specifications. Interestingly, American engineers had anticipated the possibility of German capture. Wright Field researchers developed electronic countermeasures within 2 weeks of learning about the captured fuses. The countermeasures were never needed. The Germans never used proximity fuses, but their rapid development demonstrated the depth of American technical capability. The United States could not only develop revolutionary weapons, but could also develop counters to those weapons faster than enemies could engineer them. General Patton wrote to Major General Levin Campbell, Chief of Army Ordnance, describing the new fuses with characteristic directness. "The new shell with the funny fuse is devastating," Patton reported. "We caught a German battalion trying to get across the Sauer River with a battalion concentration and killed by actual count 702. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad you all thought of it first." His assessment captured both the fuse's effectiveness and its implications. This was not just an improved weapon, it was a weapon so effective that it would fundamentally change tactics. Patton, always thinking ahead, recognized that proximity fuses would eventually spread to all armies, requiring new approaches to warfare. The Rhine crossing in March 1945 demonstrated the full maturation of the American artillery system. General William Simpson's Ninth Army prepared to cross the river near Wesel as part of Operation Plunder. The operation was planned with meticulous attention to artillery support. Fire direction centers spent days pre-calculating firing data for hundreds of targets. Survey teams precisely located every battery position. Forward observer positions were selected and surveyed. Communication networks were tested and retested. Every aspect of the artillery support plan was rehearsed until execution was automatic. The artillery preparation involved 2,070 guns positioned along the western bank. The scale was unprecedented in American military history. Fire direction centers coordinated the assault, timing the bombardment with movements of assault troops. Ammunition was stockpiled in quantities that ensured sustained fire for days if necessary. When the attack began at 2:00 a.m. on March 24, observers behind the lines reported that the entire western bank seemed to erupt simultaneously. Muzzle flashes from thousands of guns lit the night, creating a man-made thunderstorm of fire and steel. The sustained fire rate exceeded 1,000 rounds per minute, more than 16 shells every second. The noise was physically painful even miles behind the lines. The ground shook continuously. The flashes created a flickering twilight that made midnight seem like dusk. This was industrial firepower on a scale that had never been achieved before. For over an hour, the bombardment continued at this intensity. Then it shifted to rolling barrages that advanced ahead of assault troops, maintaining pressure on German defenders. The Germans defending the eastern bank faced an impossible situation. American forward observers in light aircraft directed fire onto specific targets. When German reinforcements attempted to move, they were immediately engaged by multiple batteries firing proximity-fused shells. When German troops tried to establish defensive positions, time-on-target strikes would obliterate concentrations before they could dig in. German artillery attempting to fire counter-battery missions found themselves targeted within minutes by American counter-battery fire that was faster and more accurate. The Rhine crossing succeeded with remarkably low American casualties, in large part because artillery had suppressed German defenses so thoroughly. Infantry crossed in assault boats expecting heavy resistance, but found German positions already destroyed or abandoned. The few German troops who remained were too stunned to offer effective resistance. By the afternoon of March 24, American forces had established a solid bridgehead on the eastern bank. The artillery had done its job so effectively that the crossing became almost routine. By the final months of the war, German military effectiveness had collapsed. But captured German soldiers, when asked what impressed them most about American combat power, consistently mentioned artillery above all else, not the tanks, not the tactical air support, not the endless supply convoys, the artillery, the sudden devastating barrages that arrived without warning and left no survivors, the proximity fuses that made foxholes useless, the time-on-target strikes that materialized as instantaneous walls of explosion. Klaus Werner, the young Obergefreiter who survived that first proximity fuse bombardment outside Bastogne, spent the rest of the war in a POW camp in Mississippi. He worked on a farm, slept in heated barracks, and ate better food than he had seen in years. The contrast with combat was so stark that some prisoners initially believed the comfortable conditions were a temporary ruse before harsher treatment. When interrogators asked Werner about his combat experience, he talked at length about the artillery. Not about Stalingrad's horror or the retreat through Ukraine. He talked about those minutes outside Bastogne when the sky turned to shrapnel and 3/4 of his company died without ever seeing an American soldier. That, he said, was when he knew Germany had lost. Any nation that could do that could coordinate hundreds of guns to fire simultaneously, that could make artillery shells explode at the perfect height without human adjustment, that could deliver such overwhelming firepower with such precision, was unbeatable. The technology was terrifying, but the organization behind it was even more frightening. It meant facing an enemy whose industrial capacity, technical sophistication, and systematic approach to warfare exceeded anything Germany could match. War is ultimately about breaking the enemy's will to resist. American artillery in World War II did not just kill German soldiers. It broke their faith, destroyed their morale, and demonstrated that continued resistance was futile. That is the ultimate measure of military effectiveness. American artillery achieved that completely, transforming the oldest weapon on the battlefield into an instrument of precision and overwhelming power that no enemy could withstand.